Morning, good afternoon, good evening to all the spectators on my YouTube channel, TESI, a channel for theoretical and experimental scientific investigations. Today we're going to talk about how to capture the load cell signals by using the DY510 connected with the national instrument NI6009. Alright, what you're looking right now basically is the signal capturing directly from the load cell. It has been filtered in order to avoid those fancy oscillations that can make the signal substantially fluctuating excessively. It's the same technique that is used in one of those tools that have a cost between 300, 500, even more dollar. By implementing a substantially lower cutoff, low pass filter. I use a Butterworth filter to prevent that some oscillations like those one occurring here naturally can affect the measurements. What we have also is the FFT Analyzer, the sample rate and the number of samples that I'm capturing with a window of a display of 0.1 seconds. Here I put some graph bar in order to capture the mass that I'm going to analyze, as well as the force. So we have the DC value here, which is basically that one captured by the filter signal along with the root mean square value. So how it's done basically this component, let's give a look. Control E. Substantially we have a while cycle where we have injected the signal coming from the power amplifier of the load cell, which is this one. I'll show you. The DY510, as you can see, alright, that is connected to the national instrument, and here we have the load signal, the load cell, which is this. We have basically three sample weight. We have 100 grams. Let me reconnect again the camera. 100 gram here. We have also 500 grams, and then we have also 200 grams. Yeah, I think it is visible. Yes. All right. So once we establish the acquisition parameters, which is a continuous sample in a reference single-ended, okay, on the channel A1. All right, AI0, the first channel. We push OK. Perfect. Now the DAC has been set up, and then we have implemented the FFT according to these values. The filter, I choose a low pass Butterworth third order, which is very common filter, especially for those data acquisition systems that capture this kind of signal, because the load cell is a device that basically it is subjected to different oscillations, noise, disturbance, and also such as temperature variation, and also electrical signal fluctuation due to the component, which are not ideal. They are not perfect, and nothing is perfect. So especially in the component you have several oscillations. Then you have the FFT voltage scope that we have shown before, the filter signal. I decided to capture the value in a DC waveform and then capture the mass by the calibration that I'll show you how to do it. We had then calculated the force by multiplying the mass by 9.81, which is the average of the gravity acceleration on Earth. Usually it oscillates varying the latitude by moving north to south of the pole. The gravity acceleration changes from 9.76 to 9.864. So, having said that, let's switch to the main window, push play, right? And as you can see, there is now a deviation of the value, the fluctuation that went below zero. So this fantastic load cell amplifier has a couple of screws on the back that allows you to zero the signal, the voltage. It is explicitly written. As a matter of fact, if you go right here, which is the website, okay, now you can see substantially that he has even in the other one, I think AliExpress shows that better. Look here, you can basically rotate these screws and then obtain basically the zero the signal. It's very easy, and it doesn't cost so much. It's a very affordable price, especially if you're planning to make some application like that one that I'm using right now. Obviously, by reading the spec and by doing the calibration with two simple masses, allows you to have the correct signal. Now let's rotate clockwise the screws to zero, and it's right here. I don't move the load cell because it's very sensitive. As soon as you move that one, change the signal. Okay, looks like okay, perfect. Let's make a 500 grams test. Let's put the load cell here, and I have 500 grams. Perfect. Okay. I said before that I put this calibration coefficient. This one is obtained by taking two masses, mass number 1 and mass number 2, divide the different voltage that they provide substantially in two cases. So it's the simple the slope of a straight line. Now let's take also the 200 grams like this. Let's put here in the load cell, and we have 200 grams. That's correct. And now let's take 100 grams. This one, let me see if you see. Yes. Now put here. There you go. And I have 100 grams. Okay. It has to be noticed that this load cell requires an assembly that does not want any compression on the top of the plate. Okay, let me show that better. When you assemble this load cell, okay, now the signal is going to be completely disoriented. It has been assembled in order to have this counter nut that push the support up without altering the plate where it is sitting. Because if you remove the jam nut and you tighten this part until it flashes the top of the surface, you deform basically the extensometer, the strain gauge, where those one are touched. So by the time you screw, he will alter it. As a matter of fact, if you move, it's very sensitive. Okay, if I tighten, you see that? And this is not good. Alright, so remember that when you do this kind of operation, you have to properly assemble in order to have these particular characteristics. What happens is that if I remove the jam nut and I let this component going down, the thread is sucked up, so he deforms the strain gauge. But if I basically put the jam nut and then I put in traction the thread along with this, the resultant is zero and the plate is not deformed, so the strain gauge captures only the weight of the part. Another interesting part of this schematic performed with LabVIEW is that we have an FFT. So in reality, the FFT not usable when you calculate the static load. The FFT allows you to capture the signal component when you have a loads or signal versus time, so a variation, for example, like that one, like this. But to appreciate more this, I had to expand the low pass filter up to 10 Hz. Then to visualize better, for example, 5 cycles per second, I had to increase the window. Otherwise, I'm not gonna see 5 cycles, but just a fraction of it. So I increase the number of samples in order to have a synchronous sampling, right? And then I push 5 times. See that? Look at the graph on the left side. I'm gonna expand this one so I can watch also on the right side. And I have a 5 cycle on the FFT on the bottom, as you can see, the harmonic. When can I use this? For example, assume that you are testing a motor with a propeller and you want to analyze the pulse effects that it has it has in the axis of the propeller. You can establish what is the entity of the axial force which the motor is subjected to. So this is a very interesting application. The reason why I put also the bar here is just because, for example, if I have a saturation, I can for corresponding to 1, I know I will know how much close I am to the end, to prevent that my load cell will be damaged. Usually this one reaches to 100 kilograms, the load cell that I bought. This is one of those load cells that I bought also on AliExpress. For what concerns the support for the magnet, because I'm testing a magnet force through this fixture that probably is not possible to see. Yes, this one, which I built. I led the CNC machine shop to produce the design that I made by using the CAD software. Let's see another stuff. For example, assume that I want to include graphical indicator. Oh, this is also nice. This is also nice. Yes, why not? Okay, let me see. I'm gonna put this one. For example, let's put in the mass. No, or in the force. It's more close. Yeah, why not? Suck. Let me see. I'm gonna put like 100. It will be like okay, let's reduce the number of samples. It's gonna be faster. Let's go down to this one to have more smooth operation without fluctuation, 0.5 Hz, something like this. Okay, let's see. Yeah. Yeah, very nice. This one with the multicolor bar is even better, much better. All right, what else remains to say? What is left? What is left? Let me see. Yes, it's a very interesting tool actually. I was discouraged by some other product that I found online where they declared that the amplifier, load cell amplifier, was used in the rocket hobbyist. There was a very strong fluctuation that drive me crazy. I could even use it. This is actually is very nice, and with the national instruments, it's very funny. It's possible also to implement this one with the Arduino, but it becomes a little bit more complicated, but doable. Because I gotta do some math in order to calculate the digital filter to prevent that you have all those fancy oscillations of the signal. And for today, everything is good. If you have any questions, please let me know. I will type in my email, subscribe, thumbs up if you like it. If you don't like it, you are free to express your opinion. But In any case, I like to do science, I like to do math, I like to do all these application. No matter what you say, I don't care, but I appreciate it if you say thumbs up. Okay, guys, and thank you so much, and have a wonderful night. Bye.